I think we're ready to get started, so.
All right, everybody, I think we're ready to get started here.
Okay, yeah, well, welcome everybody.
Guys, I think we're about ready to get started.
We need somebody who's got a good whistle.
Okay, I think I project a little bit more through the mask, but I might have aloneness if you can't see me through the mask. I haven't been in the building for over a year and a half, so good to be back. And it's my pleasure to introduce Stephanie Bradshaw. She's going to present her master's work today. Steph came to us in this department about a year and a half ago from civil and environmental engineering, and has really picked up on the atmospheric science and embraced that very well. She's active in the department, as you may know. She's the Welcome Committee Chair for the AOS GSA. She's also been working with the AMS Committee on Satellite Meteorology, Oceanography, and Climatology, and is active in planning for the next meeting, which is actually going to be held here in Madison next summer, hopefully. It's been a pleasure to work with her, and I'm looking forward to her presentation today. I hope you are as well. This is going to be on a model she developed for nowcasting convective storms, and we look forward to your presentation, Steph. Thank you.
All right. I think Pete had me set up with a microphone. Can everyone hear me okay in the back? No, not at all. Okay. Let's see.
You're unmuted, right?
Yes, I'm unmuted. Should I just move this closer to my face? Right, is that better? Okay. Yeah, I know my voice is kind of quiet, so started. All right, thank you, Mike, for the introduction. Well, I'm very happy to be here today and excited to be able to share my presentation with you and my master's work. We're going to kind of start out my presentation by looking at the motivation for my deep learning model for nowcasting convective storms. So after we go through the motivation, we'll then look at the details of the model, how it's working, and then we'll talk about where I hope to go with this model in the future. So without further ado, let's dive right in. Those of us that live in the Midwest are pretty familiar with thunderstorms, right? There's a lot of hazards associated with them, and this makes making timely, accurate predictions for them important because it can help mitigate loss of life, as well as infrastructure damage. So this is a big motivation for my work. The National Weather Service uses warnings and watches in order to help people mitigate these kind of hazards. And those National Weather Service forecasters have to deal with a lot of data. They have a lot of different data sources from satellites, radar, models, and they have to be able to synthesize all that information to put those warnings and watches out there. What the research group that I'm a part of does is tries to take that data, all of that data, and distill it down in a way that's really useful to forecasters. So the group I'm a part of is ProbSevere, that stands for Probability of Severe, and we have a number of different products already out in operations and in the works. Some of them being ProbSevere version 1, version 2, 3, and then intense convection nowcasting, and most recently LightningCast. In particular though, I'm working on a new feature looking at convective initiation. So that's what I'm going to talk about today, are the details of my model. But what is convective initiation? So convection can be any sort of vertical buoyant motion in the atmosphere. And I'm not interested in every single vertical plume of air in the atmosphere. We're interested in the ones that lead to thunderstorm structures. So the convection that will eventually grow into a severe storm system. This has been studied in the past by a number of different people, a number of different papers. I've listed a few here. And they've used a radar reflectivity threshold as a way of documenting when convective initiation starts. Convective initiation being the first onset of a particular threshold in radar reflectivity. So they've defined that threshold at 35 dBz for a baseline lowest tilt radar. They've also used that same threshold for a negative 10 degrees Celsius isotherm level in the cloud. However, radar reflectivity can decrease as you go up with height. That's what Zipser and Lutz has shown in some of their work. And we want to make sure we're really capturing some of the developing storms. So we've gone ahead and dropped that down to 30 dBz to try to really aim at some of the storms that are just now developing. So our definition of convective initiation is the first occurrence of greater than or equal to 30 dBz radar reflectivity at the negative 10 degrees Celsius isotherm in a cloud. To get at this question, we want to make a model that starts simple though. So we're going to actually include in the model I'm going to be sharing with you today both this convective initiation piece as well as convection that's already been initiated, so it's already above that 30 dBz mark. So everything greater than or equal to 30 dBz radar reflectivity at the negative 10 degrees Celsius isotherm is included in this model. So just to make that clear, we're not just looking at convective initiation. We'll come back to that a little bit later. We're kind of hoping to go that way in the future. So I mentioned forecasters can use satellite imagery to detect convective storms. If we look at a satellite image like this one, this is a false color image using ABI channels. So we have the red, I don't know if this blocks it or not, but our red channel is 0.64 micrometer wavelength. That's channel 2 in the ABI. And then the green is 1.6 micrometer wavelength. That's channel 5 in the ABI. And then 10.3 micrometer for the blue. And that's channel 13. That's what's shown in this picture here. If you look at this picture, how can you tell what is initiated convection, what's not convective, or what parts of the structure is going to become more severe? Let's take a look at a video to kind of see if we can tell and see some things. If you look at this right-hand side, you might see some features of interest start showing up. And then in the upper left-hand corner, you might see some more start to show up here as the system develops. There we go. So those little structures that you're seeing, they're kind of like bubbly. Those are overshooting tops. And then you can also see cloud top glaciation in satellite imagery. So these are some things that a forecaster might be able to pick up on when they're looking at satellite imagery to tell where those convective structures are happening. This kind of becomes a computer vision problem though. So we can take these kind of imagery and we can see if a computer could detect these structures for a forecaster so that they wouldn't have to sift through all this data themselves. So that becomes our question. Can we aid forecasters by training a probabilistic model to then indicate where these convective initiation and initiated clouds will occur in the next hour? In order to do that, I've developed the deep learning model. Deep learning is an offshoot of machine learning. It's categorized as deep because there's many, many layers inside of it. So we're going to start kind of simply here to keep the ultimate goal in mind of the model. So our goal is to be able to take some sort of input like that satellite imagery we just looked at, put it through a model, and then get a probability of initiated and initiation convection out. So keep this in mind as we go through the presentation. This is our ultimate goal here, is to be able to take our input data and get the convection probability out. In order to do this, we built the deep learning model, and I've broken this down into 4 different stages here for this presentation. So we'll start off by going into data preparation, then training, and then the performance validation, and look at a couple of then case testing for the model. So starting with data preparation, we know we need inputs, but we also need targets. And so we need to be able to say, here's here's some input data, then how, for a specific case, how do we know it's convective initiation? What is the target? How do we know how to tell the model is true? So we'll start out by talking about the inputs, and then we'll kind of go into that target feature. So the ABI image that I'm showing here, the false color imagery, that's put there for a reason because those are the channels that I'm using in my model. So the geostationary satellite data, the GOES 16 advanced baseline imager, where these channels are from. Channel 2 is, again, the 0.64 micrometer channel. That's at a resolution of a ½ kilometer. It's considered the visible red band, and we're using reflectance here. Channel 5 is the 1.6 micrometer channel. This is considered the snow and ice band, so you might be able to detect some more snow and ice features with this band. And it's at 1 kilometer resolution, and we're looking at reflectance as well. Channel 13 is 10.3 micrometers. This is an infrared band, and we're using brightness temperatures here. And because it's brightness temperatures and it's also considered the long wave window band, we can really see the brightness temperatures of clouds compared to the background ground. We've also set some initial limits for this model. So as I mentioned earlier, you don't want to get too complex too fast with models, because then you're not sure what to change to make it better, or if something that you are changing is actually affecting it in a positive way. So we've set the initial scope to be this region. This is the United States in Missouri, Arkansas area. And then we're set it to be daytime only. So we're looking when solar zenith angles allow for a daylight to be accessing the domain. Then the seasonality is May through August to kind of capture that kind of prime storm time period. So we need targets. So how do we know where convective initiation is occurring? Well, we kind of already hinted at this, right? So we have that definition based on a radar definition. So our targets can be the radar reflectivity at the -10°C isotherm. So here we're using MRMS, which is multi-radar, multi-sensor data. This is a data set that uses multiple radars and also different sensors like the rapid refresh model and some other sensors to produce this sort of product on the left-hand side of your screen. So this is an instantaneous MRMS radar for the -10°C level for this particular timestamp. But if we give it just an instantaneous radar, it's going to then predict what is the probability of convection at this moment. And that's not going to be super useful for forecasters. They want to be able to predict into the future. So to do that, we're taking a maximum of that radar reflectivity over an hour, and then we feed this to the model as the target for training. So we've talked about the data preparation stage. I've updated this here now, so we have our channels as our input. Let's talk about the training stage. Cholang has a book called Deep Learning with Python that was really useful to me for understanding deep learning. If you're interested in deep learning at all, I would highly recommend it, and I'm borrowing this figure from him. So this figure kind of talks about the training process. So let's walk through it. We take a set of inputs, and we want to get our predictions out. In order to get predictions, we need to learn patterns associated with the data. In order to do that, you go through layers, which are also called data transformations. And those transformations have a weight associated with them. That weight then characterizes the importance or how it wants to essentially weight the pattern that it's learned. So you go through multiple layers. This is where the deep learning comes in. So this is only showing 2 layers, but an actual model will have many different layers. So you go through here, you get your predictions out, and then you want to see how your predictions are comparing to your target data. That's what their loss function does. It measures the distance between your predictions and your targets. Based on the loss function's loss score, then, it'll send that information to an optimizer, and the optimizer then adjusts the weights. So you're tuning the weights to see how important those patterns are, and then you repeat this process. You keep going through this loop. Those are called an epoch or epoch. So yeah, you go through here until your loss function is minimizing your loss score. So that means you want to have the least distance between your predictions and targets, so where your predictions and your targets are closest to each other. Let's put this in the context of my model. We know our inputs, keep popping up frequently. We know our targets, that's the MRMS radar at negative 10 degrees Celsius for an hour into the future greater than 30 dBz. Well, how do we characterize these layers? That's where a UNet convolutional neural network shows up. This is the model that I'm using to build it, is on this UNet structure. This is very complicated, so don't look at this and get super overwhelmed. I'll kind of go through it with you. This is a UNet. You kind of get that U formation, that's where the name comes from. But focus here on the main points. We taking a set of inputs, and we want to get an output that's a probability map. We want that probability of convection. In order to do that, we have to go through those layers and those transformations in order to learn those patterns. That's what these things are doing. So let's kind of walk through some of the ones at the beginning. You can see we start with a spatial dimension up here of 1600 by 1600. We go through a convolution. So what a convolution does is you're taking windows of your data and you're learning patterns associated with your windows. You keep doing that, and that's what's building your layers and those weights. And then you come to a red arrow here. This is called max pooling. Max pooling takes the maximum between your points in your data set and produces them out. So when you get to this point, when you go through another convolution after max pooling, you're still taking the same window sizes, but because you've taken your maximums of your data, you're actually looking at a larger spatial region. So when you start out at the top here, you're learning small patterns, and then as you go through your UNet structure, you start learning larger patterns associated with your data. So you repeat this process to get more layers, learn more patterns, and then when you get to the bottom, you start upsampling, because we're at a very, very small spatial dimension now at the bottom. That's 100 by 100. We want to be able to get it back up to where we started in order to get a reasonable output out. So that's what upsampling does, kind of the opposite here of max pooling. And then we get all the way to the top. And then this purple arrow, the last convolution we're doing is a sigmoid function. What this does is it takes the information from the model and then it reduces it to be between 0 and 1, so you can get a probability out. So I know that's a lot. These things can get really complicated, and the first time seeing them, it can be kind of daunting. But overall, we're taking those inputs, and then we're getting a probability map out by going through those different data transformations and those layers. So now we've talked about the inputs, the targets, our UNet structure. I just wanted to briefly mention, for those of you who are familiar with deep learning, that we are using a loss function called binary cross entropy. Binary cross entropy, we're using this because we have kind of a binary classification going on right now. Anything greater than or equal to 30 dBz radar reflectivity at the negative 10 degrees Celsius isotherm, that is considered a yes, we have convection case, and everything under that threshold would be no, there's no convective initiation or convection case. That's why it's binary, so we have a 0 to kind of 1 pattern going on. The optimizer we're using is Atom. We're using this because it's been pretty stable in previous research. So I just wanted to briefly mention that here so those of you who are familiar with deep learning can understand where I'm getting my losses and my optimization from. Okay. So now let's talk about performance validation. How is the model performing overall? And after that, we'll learn some more about the cases and we'll get to see it visually. But let's start with some statistics. So we mentioned we had to train the model to learn different weights, and we wanted to decrease the loss function because that's the difference between your predictions and your targets, and you want that to be as close as possible. So when a model's doing well, it'll start decreasing the loss function, or the loss score, and that's what our model is doing. This blue line is our training data. So when presented with the training data, the model decreases its loss over time. And we're not seeing any jumps or anything, so that's good. Next, if we present the data with, or the model with a completely new, separate data set that's considered a validation data set, how does it do? Well, it's pretty consistent, so this is a good sign as well. So overall, it's performing pretty consistently with new data. You can also look at a receiver operating characteristic curve. This is an ROC curve. ROC curve on the x-axis down here, we have probability of false detection. Then the y-axis, we have probability of detection. So ideally, you wouldn't really have any false detection, and you would have all of your predictions occurring at that 0 mark for the probability of false detection. So ideally, you would have a line that went straight up and straight over. That is really hard to get, but our model's doing pretty well. That area under a curve that would be ideal would be 1, and our area under this curve is 0.97764. So from an ROC standpoint, our model is performing pretty well. Next, we can look at a forecast, performance diagram. To take a step back here, we have probability of detection again on the y-axis, success ratio on the x-axis. Success ratio is 1 minus FAR, FAR standing for false alarm ratio. This red line depicts our thresholds for our model. So this is a probability of 5%. This would be a probability of 40%, and on until a probability of 95%. So that's your probability of convective initiation and initiated convection. So we can see our model is not very successful at the lower probabilities, but it has a high probability of detection there. For the higher probabilities, we're not detecting them as often, but when we do detect them, they are very successful. The other item depicted on this slide is the CSI, that's the Critical Success Index. This is commonly used by forecasters, so I wanted to include it here. So it's the correct forecast over your hits, and plus your false alarms and your misses. So ideally, you would have no false alarms and no misses. You would just have all correct forecasts to be all hits. So this would ideally be 1. So we haven't hit the 1 mark, but we're closer to the 1 in this 20 to 50 probability range. Next, we can look at an attributes diagram. This diagram has forecast probability on the x-axis and conditional event frequency on the y-axis. So ideally, all of our forecasts, we want to be able to have an event associated with them. So you would have a 1-to-1 ratio between conditional event frequency and forecast probability. The red line is depicting what my model is doing. So you can see there's your slight over here, slight under the line here. So the under the line means we're having a slight over forecasting in this region. So this is between about 40% and 90% probabilities. We also have a histogram here just for reference. This is saying how many events are in each bin, bins being 0 to 10%, 10 to 20%, etc. for the convection probability. Okay, so now we've talked statistics. Let's look at case testing. What is our model doing visually? How can we see what's going on in the model? I'm going to start out here by describing to you how I've set up the outputs so that we can really understand what we're looking at as we continue on in the presentation. So on the left-hand side, these are my predictions from the model. We have the ABI channel 2, so 0.64 reflectance in the background, so that's the black and the white. Our radar reflectivity at negative 10 degrees Celsius isotherm is depicted in the reds and the red and the yellows and the greens, so primarily the greens and the yellows on this picture. This is a common kind of color bar that National Weather Service uses, so it might be pretty familiar. My contours on the map, these represent the probability, so they're probability contours. So the orange is 10%. There is a purple, it's kind of showing up a little bit more like blue, as 25%. Cyan would be 50%. Pink is 75% probability of convection in 60 minutes. And then your 90% is a dark blue. So we have an orange contour here, so that means everything within that contour is at least a 10% probability of convection. And then if you come across another contour, then everything within that contour is within that probability range. This is our original RGB from the beginning of the presentation. So I asked you, what can we see on this picture that might indicate where convection is occurring? Well, now our product does tell us where in this image we have convection occurring. Let's see kind of how it goes through time. So we watched a little video before. We had picked up on a few features down here. So maybe watch for this part of the figure, you might see some things developing. And then in the upper part, we had some development. See if we have that show up here again. Here we go. So you can see that we are predicting where these features are occurring. But let's kind of take a closer peek at this. So sometimes those small features are hard to see. So let's look at another case. This is case study 2. I'm just going to play this small video so you get a feel for what's going on, particularly noticing the upper left-hand corner here. We have a lot of development in that corner. There's a line of storms that kind of develops over time. So let's zoom in. How does this structure develop, and what does it look like from the convection standpoint? Well, this is our first contour in this region. It's a very tiny 10% probability contour at 1551 UTC. This is June 3rd, 2020. You'll notice that we have that small contour and there is no radar reflectivity showing up. So we are getting a small prediction ahead of any radar reflectivity. Next, that probability contour grows. Still no radar reflectivity. It's grown now to include a 25% contour, and we still don't have radar reflectivity. Now we have a 50% contour, and there's a tiny little green mark right here, but green is still kind of below our threshold for convective initiation. Our convective initiation is that 30 mark, so it's starting to get more yellow in the colors here. Next, we increase that probability again, and we do have a little dot of some greater than 30 radar reflectivity occurring. Next, you can really see that we've had some development, and it has kind of corresponded well with where we were seeing those contours. Just one more here for fun. You'll see that there's some more structures that had started developing on the sides as well. We'll put it all together. I can watch these kind of videos all day. I think they're really cool. Maybe not so much for everyone else, but yeah, so you can see these structures developing, and our contours are lining up pretty well with where we did have convection occurring. Deep learning models are considered a black box model. So we've just went over some examples of what the contours are showing, but how do we know what they're picking up on? When it's going through the different layers, what patterns are they learning? This is why it's called a black box, because we put some inputs in, and we get an input out, but we don't really know what kind of patterns it's actually learning. There are some kind of ways that we can look at this. This has been kind of an area that's been recently developing in AI work. We'll start out by starting with some baseline kind of analysis, and then we'll kind of move into some new methods that have been in development. So the first thing I've done is taken my initial 3-band model and will now eliminate bands. Perhaps eliminating a band from the model and then training it up might tell us which bands are most important for the predictions. And from that, maybe we can infer some physical things associated with the model. So ROC score is listed here. That's the area under the ROC curve. Our initial ROC is here. And then our least best ROC number comes when we eliminate channel 2. So if you'll recall, channel 2 has a 0.5 kilometer resolution. So something about eliminating the band that has the highest resolution might be indicating that we're not picking up on some small details that the model is learning if we get rid of it. The least is when you do not have channel 13 in there. So this might indicate that channel 2 might be most important, then channel 13 might be next, and then channel 5. Now they're all important. They all, put them all together and you get the highest ROC out. But this might indicate that something about channel 2 makes it the most important. Maybe something about cloud top brightness temperatures makes channel 13 really important. And then channel 5 being maybe the least important, but still being important because it has information on snow and ice, which can be important for a developing storm on top of the storm especially. Visually, what does this look like? Well, as I mentioned, you take that channel 2 band out, you lose some of the resolution, the fine resolution. So these contours are broader. They're not as well defined in a small region. So that really indicates how important that channel 2 band is to get some of these really tight structures that we have in the model. When we eliminate channel 13, that's depicted over here in the lower right-hand side, we start to lose some small structures. So originally in the model we had this tiny little contour showing up at the end of this line of storms. It's not there in this model. So maybe something about brightness temperatures is important for newly developing structures. Another method that we can use to get to some physical description of what the model is doing is called layer-wise relevance propagation. With this technique, you take the output prediction at a certain pixel and you run it backwards through the model to figure out which pixels are most important to the prediction at that particular pixel. So at this example, this is our second case study that we looked at. If we pick out this point in the middle of all those contours, and look at how it develops over time, what pixels around it become important for its prediction? That's the question we're trying to get at. So initially, that middle pixel has a very small probability. That's what this probability is in the lower corner of these RGB images. So at about 15%, that's the top row. And then it starts to develop. We have a 50% contour, or not contour, 50% probability listed. And then it continues to develop. You can start seeing some of those purpley, bluish, red structures on the RGB image. Those are the higher probabilities. So each channel is on its own here in each column. So when you're looking at each channel, which pixels are important? Well, I think it's kind of interesting to note here that in the original probability, or the 16, the smallest one, your pixels that are important are kind of clustered around that pixel. They're pretty close. So these are, especially you can see it here, those pixels are right around the center of that storm, with a couple of exceptions being these couple of red ones that are out here. So red being a positive relevance and blue being a negative relevance. As you continue to increase that probability, these pixels start coming towards the outer regions of the storm. Especially you can see that in the high probability, there's a lot of high relevance pixels up in the upper part of that structure, with the channel 13 maybe congregating a little bit more around the center. This might indicate that gradients in these bands, so gradients in reflectance and gradients in brightness temperature, might be important for what the model's learning. It might be picking up on patterns in gradients in these different bands. It might also be picking up on multivariate kind of patterns, so it might be picking up on gradients between the bands themselves. So this could indicate that these sorts of things are important for the model. The last thing I'd like to cover would be some comparison to some other work that's being done in the ProbSevere research group. John Centennial has been working really hard on this LightningCast model. It's received a lot of good feedback from the community, and I'm kind of excited to be able to show you the comparison here with his permission. So the lightning model on the left-hand side of this slide, it's showing contours of probability of lightning. So instead of probability of convection, it's probability of lightning. And it's using GLM data in order to get this result. So the GLM is what the targets are for this model. As you can see, the little 10% probability contour we looked at first, and this case, this is the June 3rd case, this case 2, appears 10 minutes prior to the first probability in the lightning model. This can tell us a little bit about the physical nature of our models. So lightning forms because of the electrification processes in the storm. And the electrification processes kind of stem from particles colliding, they're transitioning mass when they're doing that, and that mass has a charge associated with it. Once those particles are charged, they end up separating in the storm because of convection. So if convection is part of the reason why lightning is happening, then it kind of makes sense that if we predict convection, we might be able to get a jump on some of these structures because it's warming first. So this kind of helps verify that our model is working physically. I also wanted to just point out as well that the contours here in John's lightning model, LightningCast, they're a little bit more broad. And so we talked about that a little bit earlier with the resolution factor when we eliminated that channel 2. So if we have the GLM data here, that GLM data is a much coarser resolution than the MRMS radar reflectivity. MRMS radar reflectivity is at about 1 kilometer resolution, and the GLM is about 10. So you have a difference in resolution, so this really affects the output product. So overall, we've kind of talked about the model, we've talked about why I decided to work with this kind of project, and now looking towards the future, I think this could be a really good product to try to get towards operations, but it needs a lot of work before it gets there. Some things we're kind of looking to do, we have these initial limits to the model, so I've set the scope of the model to be in this region of the United States at the moment, so that Missouri and Arkansas area. We want to be able to get it up to the full continental United States. We also would like to be able to see it with year-round seasonality and be full daytime and nighttime, not just daytime. We'd also like to be able to isolate the convective initiation stage. So right now it's initiation and it's already initiated convection. If we can isolate the convective initiation stage, this could be a really powerful tool for forecasters to be able to see where that newly developing storms are occurring. We'd also like to just improve the model performance from a baseline computer standpoint. So improve the amount of time it takes to train the model, so reduce that time. And then also increase the accuracy of the model. And one way I'd like to maybe try to look at this would be feeding the model more positive cases to increase the ratio of positive and negatives. It's a little bit off right now. These insights, I really want to give a quick shout out to my NOAA hackathon buddies, John Centennial and Tony Wimmers, and I had the honor of working with some experts in the field to look at the code itself and see where we can improve it. I'd also like to take a little bit closer look at some of those physical insights that I was mentioning. maybe we can find more physical insights into convective initiation. So this is a goal for the future. And lastly, we would like to be able to prepare it for a National Weather Service or NOAA hazardous weather test bed setting where we can actually get feedback from forecasters to find out what's working with the way we're producing the product and what's maybe not as useful to them. Okay, well, thank you all for listening. I want to quick give an acknowledgement to everybody who's kind of helped me get to this point with my master's, especially my research team, Mike and John, and then faculty advisors, Tristan and Grant. And also, of course, the NOAA Hackathon team for their help with seeing how we can improve the model from a computer standpoint. And then, of course, my family and friends for being there to support me through this entire process. I thank you all, and thank you all for listening. If anyone has any questions, I'd be happy to answer them, or if we run out of time, to answer them later on as well. So thank you.
All right, any questions?
Ian?
Thanks so much for the talk. I appreciate the clear demonstration of deep learning, because I'm not very familiar with that. My question is pertaining to, I think, maybe more of your future work, but in terms of parsing out the difference between ongoing and initiating convection. Clearly, like in the last loop that you were showing in the previous slide, the convection is clearly, moving. So I'm wondering, how can you parse out, right along the leading edge of the squall? I would expect, if I'm a deep learning model, I might expect convective initiation in front of that whole squall line. And how do I differentiate that between the squall line moving and new cells popping up? And can the model understand that?
That's a good question. I think a lot of it comes with how you define your problem. So right now, inside of the targets, we're defining the targets as greater than or equal to a certain reflectivity threshold. If we're interested in where convection is initiating, maybe we'll have to change the way we describe the process. So instead of greater than or equal to 30, maybe we zero in on a specific range of CI values. There might be some other nuances in there that I haven't quite come across yet, because I have to keep working on this kind of problem. So investigating whether changing that threshold can give us convective initiation without getting some of the main convective structures, that's part of kind of what I hope to work on in the future. But that's a kind of an idea of where I'm hoping to kind of go off of.
Cool, thank you.
Yeah. Anyone else? Keith?
There is a question online. Jim Norris from the No Hackathon
Yeah.
asks, how many cases have you used to train the model? Do you foresee an increase over what you're using now? And how long does it take to train the model?
Okay, so I'm using about 23,000 cases to train the model, and it's training in about a day. What was the last part of this?
Do you foresee an increase over what you're using now?
I haven't really thought about that question. I mean, we have the potential to increase what we're using now. We have, at SSEC, we have quite the reservoir of ABI data. So it's certainly a possibility in the future. I think for now, to start with, maybe kind of keeping that same baseline and then see down the line if it could improve the model to incorporate more data. But if you incorporate more data, it might also increase your training time. So you have a little bit of a trade-off there. So that's something that we'll have to address as we come to it. Yeah. Cam?
Yeah, I have two quick questions. One, I'm just curious how long it takes to actually just evaluate a scene. Because just if
So are you saying if I have my model already created and then I feed it a new date? If you're looking at one timestamp, it only takes it a couple of seconds. Yeah, it doesn't take very long.
And then second question is, I know this is a little bit of part of your future work is expanding it. I'm just curious, have you tried taking your current model and just applying it to a different domain and see how it behaves?
I have not done that yet. Convection kind of changes in different parts, the way it's formed changes in different parts of the United States. So convection over mountains might behave much differently than convection over plains. So because we've limited the domain, I haven't really put it somewhere else because we're maybe not giving it some of those cases, like convection over mountains. It might not be able to see that in the early model training process. So if it can't see it in the training, it's probably not going to pick up on it in the testing. So it's an interesting thought, though. I kind of wonder what would happen. Yeah.
You have this point about investigate further insights regarding physical processes and convective initiation, and I'm just curious what the steps are that go into doing that. I guess you showed some examples with eliminating channels.
Yeah. And then a layer-wise relevance propagation is kind of a visual way you can see what pixels are important. But this is still kind of an area of development in AI. It is called explainable AI. So how can we explain the patterns the model's using? And I'm hoping to kind of look into some new explainable AI methods and see if they could offer more insight to the physical processes besides what I've already done. And then also, if we increase the model, expand the model to continental United States, like I was mentioning to Cam, since we have different convection kind of structures that happen in the United States, maybe the way the model's behaving in different areas of the United States could kind of give us some more physical insights. It's kind of what I was getting at. Yeah, if you have any other suggestions, I'd be happy to kind of hear them.
Very interesting question.
Yeah.
I don't know much about deep learning, so.
Okay, yeah, no, it's kind of exciting to be able to work on this as explainable AI and atmospheric science is becoming more common. In the back.
Yeah, I'm just curious if you can comment at all on how this performs against like an object identification tracking method, and then also how you might be able to use something like this to connect to like relative thermodynamic and dynamic influences upon convection.
Yeah, so we've actually kind of investigated a little bit with object tracking. WIDS2 is the program we were kind of using, so advanced watershed kind of outlook for it. When I compared what we were doing with WIDS2 to the maximum reflectivities, we were getting a little bit better performance, but the WIDS2 stuff is still working. So I might end up going back to the WIDS to maybe see if that would be more appropriate for isolating the initial convection. But I'm not sure if I could comment on like how amazing it is to do radar reflectivity versus object tracking. I don't think that's really applicable. I think it kind of really depends on what case you're using and how you want to define your problem. What was your second question?
Oh, just if you can pull any insight from like the environments.
Oh, yes. So I'm strictly using ABI data for my project right now. But you could include things from the like temperature profiles and other things. I haven't done that, but I know that it's possible. And yeah, so if you're interested in that, maybe if I get down the line and decide to try that out, we might be able to chat a little bit more and see what happens. So,
It seems like the object tracking might be, the object tracking might be useful in the convective initiation, defining which are new blobs versus.
Mm-hmm. Yeah, so we've been starting to work with that. We had kind of shelved it a little bit so for the purpose of a master's, but for PhD work, it might be really useful to go back to that.
Yeah, so I'm kind of wondering about if the machine learning model is kind of picking up on the slope of the 0.64 micron channel. So like as you kind of get convective initiation, the clouds get thicker, and I was kind of wondering about how the radar reflection threshold kind of ties into that. You know, and how sensitive the model is to the radar reflectivity threshold you give it.
Okay, I think that's a really good question. I haven't looked at it a lot yet. I don't think I really have a good, robust answer for you. But based on kind of what I was talking about with eliminating the bands and looking at where the layer-wise relevance propagation tells us the pixels are, you can kind of tell that it's inferring something about gradients, which I think is what you're talking about with slope, right? So gradients within the band itself. So I think it is kind of picking up on them, but it's not clear to me yet how you could alter the reflectance in a way that could change things. Maybe we should talk later. Yeah. I'm gonna go in the back first, Pete, if that's okay.
Yep.
Gerald?
Do you think adding another band would like improve performance, like a fourth band or maybe
That's something I'm hoping to look into. I know with the LightningCast model, John does use another band. So right now I'm not, but I would like to look at that. I think, Hannah, did you have a...
Yeah. Can you go back to your ROC, AUC values when you were comparing the different, taking the channels out, eliminating channels?
Oh, I think I'm way too far, aren't I? You want this one?
Yeah. So when I look at those look basically the same to me for somebody who has an untrained eye for ML things.
Yeah.
And I was wondering how you kind of know that those are different enough that the changes that you've made actually matter to your model. I know you showed the sort of pictures afterward where some things kind of look a little bit different, but when I look at that, I'm like, I don't see the difference. And so I'm just curious if you could speak to that a little bit, because I'm really interested in that.
To be honest, I haven't thought about it. But I think that now that you say that, I think that might be something worth looking into, the statistics part of it. One thing you could do is, so when you train the model, you can kind of give it different training data sets. You can randomize the data that you give it, and then that produces many different results over time. So kind of what I'm thinking of with what you said is if you run it on a lot of different training data sets and compare the numbers, maybe you could then use some sort of correlation coefficient to see if there's a significant difference then between those bands. That's kind of what I'm thinking of, but if you have other ideas, I'd love to hear them.
No, I definitely don't.
Okay. Brad?
So it's kind of was clearest in your last group. There you show your probability kind of leading the storm.
Yeah.
Like Ian was saying. Have you looked, but in most of the loops, it looks like the probability is centered on the radar reflectivity. Your definition is within 60 minutes. Have you looked at what kind of lag there is between when you have a certain probability and when it's real lag?
I have not looked at
Or
that.
is it more, in some cases, it seems like it is preceding the actual signal on the radar, but in most cases, it's on top of it.
Yeah, so I think it also depends on how the trajectory is moving. So if you have a convective structure that's moving pretty well within an hour, then you might be able to get those lead times. But if the structure kind of develops and then quickly dissipates, you might not get much motion. So I think that might be interesting to look at. I haven't really done much with that yet. It's a good thought though, thank you. Sorry, I can't tell who's who, guys. Angel, right?
Yeah,
Okay.
By the way, like, I wanted to say that this is like a really, really nice talk, very well organized. I always really appreciate what the information is condensed in a very accessible way. I'm not an expert in machine learning, so I really appreciate that. With that said, I'm just like totally curious how slide 7, you showed an animation with like the different colors. Like, my question is like, did you make that? Did you download that in the software? Because I like it and I would love to use it for my class. That's really my question.
Slide 7?
Yeah, this one.
This?
Yeah.
I made these.
Oh, you made it. Okay, cool.
Yeah, in Python, I use SatPy. SatPy is the language I'm using, and you can specify what bands you want to be what color, and then it'll output these sorts of images.
Did you choose the color for that?
Well, it's red, green, blue for the RGB, so I picked which bands were gonna go where.
Oh, cool, nice. Oh, I like it, because I like, you can see the shallow and, medium of my color grade.
Mhm.
It would be very nice to, like, for discussions of, like, all the deep convection. That was it. Wondering how you did it.
Okay. Anything, Newell?
For the eliminating case, why did you decide to eliminate one channel instead of just doing your training your model on just one channel? So you're taking one off, but
Yeah.
why don't you just training on one channel?
I think it's just because it didn't occur to me at the time, but I think that might be useful too. I will keep that in mind. Thank you, Newell.
And I got another question. So you compare the lightning prediction with the convection initiation model. Is it possible to feed your model into the lightning prediction model? So because you're seeing the convection initiation ahead of the lightning occur, would it be beneficial for the lightning prediction to have it?
So you're talking about kind of stringing the model together, like two models together?
Yeah.
I have no idea. Yeah, I don't know if that's possible. I have not thought about that. Thank you, though. Yes?
If your model is looking at a like fixed spatial scale like this, does it develop a like spatial difference in convection probability? Like if you had a mountain range or something, like would it be more likely to think that convection will occur there? And
It could be very well that it is learning patterns like that. Like it's black box, right? So we're not 100% sure exactly what it's picking up on sometimes, but that's why it could be very hard to expand. If I gave it all the same information that I'm giving it now and then take that model and move it somewhere else, it's probably not going to work very well. So expanding it to the rest of the United States, what I'm going to want to do is kind of bin the United States up and then randomly sample from those sections to give or a certain number in one bin, a certain number in one bin, and then randomly pick them out so that you can really make sure you're representing every case that you want to give it, because it's a computer vision problem. If you train the model with it and then you give it something completely different it's never seen before, it's not going to know what to do with it.
And then a related question is, do you have problems with the edge cases? Like, will it predict convection near the borders? Or
I haven't noticed any edge problems. That being said, it could be happening, and I just might not have found it yet. Carrie?
Yeah, so I remember you were talking about how in that figure you would like basically generate the weights for all of the channels.
Yeah.
I was wondering, did it give you individual like did it give you like for this or for the aggregate of all the cases, this channel is this way, this channel is this way, and this channel is this way?
Yeah, so it's not so much the channels having weights, but the layers, the patterns within the layers having weights. So the weights, the channels then get, the data that you put into the model gets transformed. So that's why it's called the data transformation for the layer. So when you're taking the little windows of data, it's learning patterns and then associating weights with those. So it's not so much you're assigning the weight to the channel itself, if that makes sense. But at the end, you can print out what the final weights are for the model. Yeah, but in my case, there's so many layers. I'm not sure if we like pages of weights. So, yeah.
There's two quick questions from online. First of all, how do you accommodate the different spatial resolutions of each channel at the start of the UNet? And the other one is, how do you know that the 3 channels that you selected are the best?
So the 3 channels I've selected, we're selecting them kind of based on previous work that's been done. These kind of channels have been shown to really kind of represent thunderstorms in a way that's useful. We're dealing with what was the last?
The spatial resolutions before you put them in the UNet?
Yeah, so you have to kind of resample the data sets in order to get them to align with each other. So we're resampling. That's what he's asking.